So hello everyone. We have a presentation of Elif. She's a PhD student at Sorbonne. She's presenting a paper that was accepted in Globcom. So she's presenting this work that we did together with also Nur and Anastasios.
I should continue. Hi again, everyone. I'm Elif. Can you hear me? As Francesca said, today I will present our paper that was published in the Globcom conference last year. And in this paper, we propose a resource deep reinforcement learning resource allocation for the synchronization in the environment. And we had colleagues collaborating with us, Chila, from Nokia, Anastasios, and Francisco from Ebru and And to begin, before beginning my presentation, I will briefly explain what I will talk about today. I will briefly explain what is a metaverse and what is digital twins, and I will briefly explain the challenge that we are addressing here. I don't know. It's not open from there. Okay, yeah, this is better, I think. Then I will explain the modeling of the system and the formulation of the problem. And then I will show a bit from the simulator that we implemented to test our solution. Then I will show you the results that we obtained. To start with, what is Metaverse and what are digital twins? Digital twins are the virtual replicas of a physical environment, like something, for example, a meeting room like this, or a bigger smart city, or a smart building, a smart factory. And in digital twins, there is a constant data stream between the physical twin to the digital twin. And a metaverse is actually a shared virtual space where the users can interact with those digital twins through some immersive experiences. So a metaverse can be presented as a convergence of the physical and the digital environment, and we can interact with digital twins through these metaverses. And the digital twins, they enable us to do some remote interactions or remote controlling on the on the metaverse. So here the key requirement is that there needs to be a near real-time synchronization, and the digital twins must accurately reflect what is happening in the real world on the digital twin. So we see here that the synchronization happens through the sensor data stream from the physical twin to the digital twin. And Metaverse has lots of different application areas in different domains. For example, in virtual reality gaming, where the digital twins, they can provide some room scale tracking or obstacle detection to keep the players safe in their physical environment. Or in more like industrial settings, the digital twins, they can enable, as we said, like remote interactions to the factory floors or the robotic systems in the factories. And also in autonomous vehicles, they can provide us some real-time information about the traffic or the conditions in the road. So here, the key challenge that we try to address is that the digital twins must be accurately reflecting the physical environment and all the physical changes in real time. This is our goal, but we are facing some constraints, some limits on this. For example, the first one is the user request. They cannot tolerate long delays. So whenever a user sends a request, it needs to be served with the minimum latency. Then we have limited network and computational resources, and like we have limited bandwidth and limited computing capacity in the base station, and those are like finite, and they need to be shared. Also, we have a varying service demands from devices and sensors. So sometimes like the traffic is high, the number of users are higher and they are requesting more, and sometimes they are lower. So there's a dynamic change in the pattern of the traffic. So here, the key question that we want to answer is like how we can split those limited resources among the sensor data, the sensor flow, and mobile devices, so that we can achieve a real-time synchronization, as well as we remain a high throughput overall the system and the low latency. If we look at the literature work that has been done on the topic, there are lots of work done for the synchronization of the digital twins. They mostly propose a decentralized framework or predictive synchronization scenarios, techniques, and some game theoretic approaches. But the focus on all of these work is mostly the synchronization delay between the sensor data and the digital twin. The importance is the data freshness of the data, sensory data. But those works, they don't consider the user request part and the resource allocation part. Another part of the literature, they talk about the resource management. They propose some task offloading approaches or latency minimizations in 6G. But on that side, it's mostly user-centric, and they don't think about the sensor data and the freshness as well. So here we see that none of those works that we have seen so far, it's trying to jointly optimize the user request delay, the synchronization delay, and as well as the whole throughput of the system by doing any type of dynamic resource allocation. So in this paper, what we propose is like there are 4 unique contributions that we add. First of all, we propose a multi-objective optimization framework, and in this, we try to balance the latency, the end-to-end latency of the user request, the synchronization delay of the sensor data, and the overall system throughput. Then we propose 2 different age of information metrics. The first one is the age of request information, and this will be the total service delay for a user request. The second one is the age of sensor information, and this measures the freshness of the sensor data, which I will explain both of this later in more detail. Then we propose an adaptive deep reinforcement learning solution using the PPO algorithm. And lastly, we built this simulator to test our solution. And this simulator has been extended from another simulator called Mobile Lens. But this was just for associating users to the base station. We took this and we applied all of our components and our contributions to make this MetaLore simulator. Yeah. So about the modeling of our system. I can do it. Yes. So in the system architecture, we have 4 different components. Can you hear me? Yeah, this is better. In the architecture of the problem, we have 4 different components. The base station, and coupled with a MAC server, an edge server. We have stationary sensors that are distributed around the base station, and they are not moving. And we have mobile devices that are also distributed around the system, but they are moving. They are not stationary. So overall, this is what we call the decentralized metaverse, and it represents a sub-metaverse. So we take the whole physical region and divide it, partition it into different sub-metaverses, and that's what we call a sub-metaverse. And then we have a two-stage queuing system in the device side and the network side. So on the device side, each device, each mobile device and each sensor, they have a local communication queue. And those queues, they buffer the data packets that those sensors and the user devices generate. And then after they are transmitted, we have two computation queues in the server side. So one of them is for the user devices. The other one is for the sensor data. So we buffer those packets until they are processed in the server. And then the traffic models. So both the user equipments and the sensors, they generate packets. The users, they request service randomly following the Bernoulli distribution, but the sensors, they periodically generate data. Then for the user equipments and the sensors, they have a stochastic packet size and processing load of the packets, and they both follow the Poisson distribution. So this random generation of the request in the user side and the varying packet size and the processing load, they create a dynamic traffic here. And lastly, the resources that we have on the system. We have communication resource, which is the transmission bandwidth in the base station. And we have the computation resource, which is the processing capacity of the server. And those resources are finite, and that they need to be shared among those two different data flows. So they should be allocated among the sensors and the users regarding this split, alpha and beta. So the users, they receive, if we say that the users receive the alpha share of the resources, let's say the bandwidth resource, then the sensors will get 1 minus a share, alpha share of the resource. And for the processing capacity, if we say that the users will get beta share of the resources, then 1 minus beta will be for the sensors. So we are splitting the whole resource into sensors and users. But here, as we said in the previous slide, there is a dynamic traffic here. The key challenge here is that we need to split those resources dynamically every time as well because of the changing pattern of the traffic. So let's, like as we said before, like why did we said we need to dynamically share these resources? Because we have dynamic traffic, and if we don't apply this dynamic split, if we use fixed splits, then the splitting of the resources won't be efficient. So if we have highly variable traffic on the user side, the sensor part is more regular compared to the user side, but still we can have different numbers of sensors. So at every time the state is changing, the traffic pattern is changing. So aside from the fixed split, we need a dynamic and state-aware resource splitting. So again, if we look at this example, if we use a fixed split, like we say 50-50, like half of the resources are for sensors and half of them are for the users. So if we have many user requests, then maybe there won't be enough resource for the users, and there will be more than enough resource for the sensors, then users will start waiting too long for their request. On the other side, if we have more than the usual sensor number and we have too many sensor updates, then the sensor data will be delayed and we will have more stale sensor data. So that's why we need an adaptive splitting here. The fixed split is not working for dynamic environments. So to measure the performance of our system, as I said, we introduced two different age of information metrics. The first one is the age of request information. Age of request information, it measures the end-to-end service delay for a request. And it has four different components: the queuing delay at the device, then the transmission delay to the base station, the buffering delay there, and the processing delay at the server. So overall, the total time for these four components, it gives us the age of request information. We will also call this end-to-end delay of the request. And as you can understand, if we have a lower age of request information, then it means that we serve the request faster. If the age of request information increases, that means that we are getting slower at serving the users. Then we have the second metric, age of sensor information. And it measures the synchronization delay for a request. And it's the time difference between the service request generation and sensor data generation. So we made this time plot to show what does it mean. So as you can see, the sensor data, they are generated here periodically. And here we have a service request. This is the transmission side. And on the processing side, since the resource, it depends on the resource allocation, they are not processed right away. So when we are waiting to serve the user, we check the latest available data from the sensor side. And like, as we can see, there are more fresh data here generated on the sensor side. They are not processed yet. So if we look at the processed ones, the latest one is this one. It is the most recent available sensor data. And to find the age of sensor information here, we go back and we take the time difference from their generation, like T1 minus T3 or T3 minus T1. And this gives us the synchronization delay. Also, we can say age of sensor information. And as you can see, if we have a lower age of sensor information, it means that we have a more fresher information from the sensor data. Yes. So this is a very quick explanation of the whole system. So we create a request. It waits in the queue locally, then we transmit it to the BS, and it waits at the base station. Then it gets processed in the MAC server with the latest data, and it's served. So this is like a summary of the system. And this is the challenge that we are trying to solve. The resource allocation. As we said, there are two different data flows, the user request and the sensor updates, and they are both competing for the two resources, the communication and the computation. resources, and we want to split those resources among those two flows to keep the users happy with a low request delay, end-to-end delay. Then we want to keep the synchronization fresh with a low synchronization delay, and we want to maximize the throughput, the overall throughput. And we know that the fixed split is not working because of the dynamic of the traffic. So why, about the problem formulation, why we formulated this problem as an MDP? First, it's because it's sequential. So repeatedly, we need to decide on the split ratio of the resources among sensors and the user requests. Then we have randomly arriving user requests and changing user requests and sensor arrivals. And the optimal split at a time step, it depends on the current congestion of the computation queues. And the current decisions, they affect the future queue states. And here the challenges, again, we said we have random arrivals and dynamic traffic, and we know that the fixed policy wastes our resources and it's inefficient. And it's not, and it's ignoring the current load. So we need to propose, we need a state-dependent decision, which will learn an optimal policy to maximize the long-term cumulative reward. So what are the components of the NDP? As the state space, we take the computation queues, the length of the computation queues at the edge server. So the buffering at the queue length, the queues. As the action space, we take the resource split, so how much computation and how much processing power is allocated to sensors and users. And as the reward, we have, again, two components for the rewards, the synchronization reward and the latency penalty, which I will explain in the following slide. And we have the transition dynamics, and we have episodic training, and this is the objective function that we want to maximize with the policy. So about the reward function design, as you can see, we have two different components. The reward that we give for the freshness of the sensor data, and the penalty that we give for late service requests. So the synchronization reward, we have a base reward called C1 here. And with this other symbol, eta, it is the discount factor, and it discounts the base reward. So based on the age of sensor information. So we calculate this reward for every served request. So if a served request has an age of sensor information or the synchronization latency as 0, then it will give a reward of C1, like it will get the whole base reward. But as the age of sensor information starts increasing, then this factor of eta, it will discount the base reward, and our base reward will start decreasing. So as we have a lower eta, if we have a lower eta value, then it means that the agent is forcing the policy to prioritize more fresher updates. On the delay penalty side, we have a base penalty of C2. So again, we calculate, like we compute this penalty for every served user request. So for every user request, after it's served, we check the age of request information, like the whole end-to-end delay of the packet. If it's more than a threshold that we decided before, if it's more than this threshold, then we give a penalty for this user request. So if we choose a higher value for C2, then it means that the agent will learn to avoid the delay, end-to-end delay for the user requests. So in this reward function, what we are trying to do is to design this reward function with two hyperparameters, which is the eta value and the C2 value. So by changing these values, we are trying to design the reward function and to try to shape how the agent is behaving. Also, in this problem, we have, as we said, we have three different objectives that we are trying to maximize, but these objectives are competing with each other. It's the synchronization, the throughput, and the latency. So if we look at the trade-off between the synchronization and the throughput, like if we allocate more resources to the sensors, then it will obviously get a better synchronization for the sensor data, but then we will get a lower user request throughput. And on the latency and the freshness side, if we start prioritizing the users, then they will get a lower end-to-end delay. But then again, we will start having a more stale sensor data. So we try to find the optimal split at every time step that because it changes with the dynamically changing traffic from the sensors and the users. And it also affects the queuing in the edge servers, the computation queues. So we propose here the deep reinforcement learning, and we use the PPO algorithm here. And then, like I said in the beginning, we developed this simulator to test our solution. So initially, we only had the base station and the user devices, and then we implemented those sensors that are blue here. They are stationary. And we have those mobile users. They are moving around, and they are all served by the user at the base station here. And here we see the metrics, age of request information and age of sensor information, and we see the allocation step by step here. So in this setup, we used only one base station and one MEC server, as we said. And we used 10 mobile user devices and 15 sensors. And we had a bandwidth of 100 megahertz and processing capacity of 100 computing units. And for the training phase, so we had two different phases. And for the reward function, so we have two constants, like the C1 is the base reward, as we said, and the delay threshold is 2 time steps. And we are trying to tune the parameters, the discount factor and the delay penalty. So in the first phase of the trainings, we didn't use any penalty. We just focused on the synchronization and the throughput trade-off. And we took the eta starting from 0.9 until 0.4. We tried for every different eta values to see what is the how does the agent behaves. Then on the second phase, we add the penalty. We said we take the C2 as -1 as the penalty. base penalty. And then we again use the same eta range from 0.9 until 0.4. And then at this phase, we looked at all synchronization, delay, and throughput trade-offs. Then we compared these with the baseline scenario, which is like a fixed split, fixed allocation. And we started from 0 until 1, so 0.1, 0.2. So we tried all the possible splitting ratios for the computation and communication resources. I put a demo here of the video. I think it's not working in the PDF. We will have time. I will show the video at the end. I will continue with the results and then I will show you the video. So here we see two plots, like in the second one, the other one. This first plot, this is the comparison of the two trade-offs, the throughput on the y-axis and the synchronization delay on the x-axis. Those colored points, they represent the fixed splits in the baseline scenario. And their color and their size, it changes based on the split ratio. The color changes based on the bandwidth allocation, and the size is based on the computation allocation. Then we have those red dots here, and they represent the different trainings from the using different eta and C2 values that we choose for the discount factor eta and the penalty value C2. So we here see that it's a synchronization delay versus throughput. So if we go to the left and if we go to the higher, then we will get a better throughput and better synchronization delay. And we see that those points A, B, and E, they lie on the Pareto frontier of all data. So which means that if we try to have a better throughput, then we need to sacrifice the synchronization. Or if we want a better synchronization, then we need to sacrifice the throughput. So we see that the DRL points are almost as good as the fixed splits, and in some parts they are even better than the fixed splits. And the points A, B, and E with the eta value 0.9, 0.8, and 0.5, they represent the optimal trade-off here. And as you see, if we try to tune the reward function, if we use a higher eta value, it starts favoring the throughput. And if we lower the eta value, like going from A to F, A, B, C, D, F, it starts favoring the synchronization trade-off. Then we see that the point CD, they sacrifice the throughput to make the synchronization delay better. Here, the C and D value, they have a lower throughput, but they have a very fairly better synchronization delay. And on the second plot, we see the end-to-end delay on the x-axis and the synchronization delay on the y-axis. And again, we see the DRL points as the red ones. And at first, on the dots A, B, C, D, and E, F, we don't use any penalty. And we see that they achieve a better trade-off on the end-to-end on the synchronization side. And when we start adding the penalty, the points K and L, they shift their focus from synchronization to more to the end-to-end delay to minimize the age of request information. So here, the advantage that comes from using the deep reinforcement learning is that we are not trying to find the best allocation for every every traffic type. So since we know that the traffic is changing dynamically, we shouldn't go and look for the best allocation all the time. With this DRL, it helps us to find the best allocation at every time step, depending on the queue length. So this was the end of the paper. What we want to do later with this work in the future. We want to, first actually, we want to test this in a more dynamic scenario where we have changing number of users and changing arrivals of the users. And sometimes they are coming maybe and they are leaving the scenario. And then we want to also test the association of the users. Like at first we want to move this into a multi-base station scenario. So instead of just one sub-metaverse, we want to test this on multiple sub-metaverses and see how the resources are being shared and how do we do the user association and the handoffs in a multi-sub-metaverse environment. So we want to go toward a more distributed and low latency metaverse and resource allocation. So that was it. Thank you for listening. This is the link for our simulator. If you want to check it out, you can find it here. And if you have any questions, you can have a discussion, or maybe you can send me an email. We can discuss.
Thank you.
You are targeting to somehow minimizing the latency.
Yes.
But there is a class of real-time systems where you have what is called hard real-time. So you cannot go beyond a certain threshold. So you can think, for example, of a road scenario. If the light goes to red 1 second late, even if it's the best effort, then some people die. So adding this kind of constraints, how would it fit in your framework?
So maybe we can focus on the delay threshold that we choose. But yeah, this will be more on the reward side. Maybe we can penalize the latency more with the value that we choose for C2. But like as you said, it's like we cannot make it the best, I guess, more real time. Yeah, I don't know.
Thank you.
Other question in the room? Are there some question remote on the Zoom?
Are there any, or
I'm just asking for two people. So apparently I don't. So yeah, no, apparently there is no question.
Yeah.
And so thank you again.
Thank you.
Yeah, sorry for the people, there is a demo that will be shown. Good.
A second. Yes, it's finished. I'm just trying to show the demo of. Very good on the big screen. So yeah. Here we see the moving user devices and the sensors, and here we see it is not the trained version, which is just the randomly picking the list. This shows the computation allocation. This is the bandwidth allocation, and like at every time step, we calculate, we compute the delay, the synchronization delay, and the end-time delay for every user request. And like we said, it's just one sub-MetaLore, and the users are defined at the beginning of the scenario. We have the same amount of users during the whole episode. It doesn't change. Like for the middle step, we want to make it a more multi-destination scenario with users arriving and leaving the sub-MetaLore. Yes. Sorry.
So yeah, I have another question. So here, the request of the users, do you assume that they are of the same size in terms of?
No,
Okay.
they are not the same size, but they share the Poisson distribution. So there's a mean. So it's going around the mean value. It's usually different, but like very close to a mean value.
Okay, because I don't know if that is relevant for your research, but if the requests have not Poisson distribution, maybe they have a long tail. You have very long requests, you may have very long requests and very short requests. Do you think that the reward function that you have done, that you have provided, may privilege very short requests so that they minimize the latency, and so long requests may be penalized artificially? Again, it's something may not be of interest, but
yeah, it might be a good idea. Maybe like what we do here is if we have a longer request, let's say, I think it's what you mean. So based on the allocation, if we cannot transmit it in one time step, we like divide it into multiple packets, and then like depending on the allocation, it waits on the buffer on the queue. So it gets transmitted at in a long time. And then once it's finished, then we compute the whole end-to-end latency and the synchronization delay. So yeah, it might have an effect on the reward function, I think, yeah.
Actually, you mentioned your work actually for your multi-objective problem formulation. You will detail it, and then you said that the solution is you wanted to use reinforcement learning using the PPO algorithm. My question is more about is it really the reinforcement learning the best solution, or why did you choose this? Or it couldn't, for example, there is no another algorithm, why reinforcement learning and why PPO? And yes, it's
So we choose to use the reinforcement learning algorithm because we formulated as a dynamic problem, dynamically changing problem at the MDP. So we thought like it could be a good idea to use the DRL, but we also wanted to use some other optimization techniques, I think, but we didn't work on that. We just wanted to do with the DRL.
okay. And in the literature, we could find, for example, the same objective or problem multi-objective with algorithm other than reinforcement learning.
So sorry, I didn't.
I ask about, for example, the literature for the same, not the same, but similar multi-objective problem. Is it just, is there another algorithms used to optimize or find the solution?
Not for the specific problem, because I think there are no other work that formulates the problem like us, like
Okay.
because we said we have two different data flows and we want to allocate the resources by splitting them. So I didn't see any other research
Okay, thank you.
based on this problem.
Okay, thank you. And about the training, because you detailed that there is phase 1 and phase 2. For example, first you just fix, I remember maybe ETA, something like
yes.
that, and then you change the other one, and in the inverse. And for the training, it was in the first, for example, synchronization versus the throughput. So here we can say that you for this training was needed, you were needed for the reinforcement learning algorithm.
Yes.
Okay. So,
Also to design the reward function, which value is more suitable for our reward.
okay. And for example, because we could find, for example, phase 1 and phase 2. And for example, if we change, we have just one phase or we have much more than these two phases, the result will change in this case because it's based on this training.
So the difference between phase 1 and phase 2 is in phase 1 we didn't use any penalty. So phase 1 only focuses on the synchronization and the throughput. So it doesn't care about the end-to-end latency.
Okay.
On the second phase, we added the penalty to
Yeah.
see how it changes the whole optimization problem. Because we also add the delay, which is the end-to-end delay now. So we did trainings for the same range of eta and with the penalty to see which reward function fits better for our scenario.
Okay, and the result or the optimized result is based on this training phase. So how much data we have, or how much phase we have, and what are really the steps in each phase.
I don't know if I understand it correctly, but so with these red points, they represent each training in these two phases. So
Okay.
the points A, B, C, D, and F, it's from the phase 1. The rest of the points are from the phase 2.
Okay. Okay.
Okay.
But okay. And for the result of reinforcement learning, where it's because
So
we have training here and there.
yes,
In the two phases, but what I question was, for example, I don't know really the reinforcement learning, so really I don't know, but it's like we have the optimized synchronization and the throughput according to the different data sets that we have. So it's more here training, something like that.
yes. So based on these changing to different values, we trained almost, I think, 10 different models. And we use those models to, on the same scenario,
Okay.
10 times, I think. And then we measured the overall synchronization delay and the throughput, and also the end-to-end delay. And that's their position comparing to the fixed splits.
Okay, thank you.
I hope it was clear.
Okay.
No other questions, I guess. Thank you.